Uh, so I have a few general questions to prod the panel discussion. As usual, attendees should feel free to add more in the chat. So the first one, and it was prodded by the first talk, but I think it has impact on the other ones as well, that raised the issue, the identifiability issue. So in the context of the first talk, for example, somebody in the chat mentioned Marcus Hooter's scheme of universal computation. So how do we deal with that? The fact that there may be very different computational schemes that cover human cognition or general intelligence. How do we validate them? And Rick and Andrew had touched on that toward the end of their talk. But in general, how do we frame that? And I won't necessarily force a round robin through the panelists, but the panelists should feel free to jump in where, whenever they want. But if nobody jumps in, I'm going to force a round robin. John, you seem ready to jump in. So how about you do?
Oh, I'm not at all ready to jump in. But I think that at least within what I was talking about, there was no possibility of a single theory or a single method or a single algorithm that would apply for all of the different things that human intelligence can cover. So I certainly would fall on the side of saying one needs to find the appropriate method for the appropriate kind of problem, and that what the brain is doing is learning how to manage having this large number of methods at its disposal. I don't know if that's how that fits into the question exactly, but I'm certainly not on the side of having a single theory or a single method.
Christian, I think I didn't understand the question exactly. Maybe can you just restate it one more time?
Well, so you can show that, let's say, for example, that reinforcement learning can account for human-like intelligence, or even higher than human-like intelligence. So is that necessarily the right theory? How do we constrain which theories we consider for cognitive architectures and cognitive science and human and artificial intelligence? How do we think about selecting between theories, or are they all good? Do we not care to select and validate in that way? Are we just exploring a broader space?
Well, I think from a cog-sci perspective, we engage in empirical science. We test predictions of the theories, and I'm not sure that there's a special problem for computational theories that don't show up in other parts of psychological science. I think what cognitive architectures as an approach, we tried to make this point at the beginning of the talk, emphasizes that is not emphasized sufficiently well, maybe in other parts of cognitive science, is a concern for functionality. And so I think as long as machine learning is producing interesting advances in functionality that are achieving human level performance, and we don't have a whole zoo of other alternative approaches that are also achieving human level performance, then I think it warrants attention, until we get to the point where, we've got 100 different architectures that achieve, grandmaster level chess, or can, learn how to walk, or engage in visual search or language. Then AI and cognitive science will part ways, maybe.
Good, thank you. Sean or Chris, do you have anything to add?
I could hazard saying something here. I guess one of the things that I'm a little skeptical of is, the replication of behavior. I think that if you're really trying to substantiate a case that the mechanism you have is human-like, I'm not sure that the simple replication of behavior is sufficient. Now, I think we probably have a long way to go before we get here, but one of the things that would be more convincing to me anyway, is if you built an agent and then you tested something on that agent where you learned some novel thing. So you have a new hypothesis that then you can go back and test on real humans, some new knowledge that you didn't know. Then you kind of strengthen your theory a little bit by saying, well, this was not predicted. I'm not just replicating behavior. I'm trying to create an agent that produces behaviors that may say something new about human beings. And so through that cycle, I think it's a little more compelling than just the replication of behavior.
Sean's exactly right. I think that this classic scientific method has to apply here, is that you need to be able to test not just the explanatory power of a theory, but the way, whether or not it predicts new knowledge that then can be experimentally verified. And then you refine the theory. So I would agree with you completely, Sean.
Thanks.
So to push in, go ahead.
Oh, okay. There is a subpart of the identifiability problem that that looms large for cognitive architectures, which is the extreme flexibility of programmable architectures. They admit to an infinite variety of strategies, and it's crucial, therefore, that there is a way found to select strategies so that you don't have the flexibility to choose architecture freely and choose strategy flexibly. And reward maximization can be a step in the right direction for that.
Thank you. So to push in one particular direction on this, so the issue of scaling and complexity, as Rick mentioned, so deep reinforcement learning has been insanely successful, but it's also used insanely intense level of computation often. And John mentioned explicitly in his talk the issue of complexity, of the fact that we have limited time, limited power. How does that play out? And in particular, as a computer scientist, one thing that's always been just incredible to me is that the theory of computation shows that what is hard, so somebody in one of the chat mentioned PNNP, what is hard in one computing framework is hard in all the others. Is that the case in theories of intelligence and cognition, or are different theories, different approaches weighted differently so that in some domains, some might be really successful, but not in other domains, and vice versa?
Well, I would say that, I mean, it's not the domain, it's really the size of the problem. It might be the case. So in the early days of convolutional neural networks, Jan LeCun and others were working on extremely tiny images. That's the only things they could actually, compute at the time. Now this image size is increased, but it still does not increase, to the level that the human retina allows you to get. So there is an issue of the scale of the problem. It might be that for useful applications, the size of image that your iPhone or whatever can get, it works just fine. And from that perspective, it's not a question, but it really depends on the scale of the problem that you want to address. The theorems, until someone proves differently, that have appeared in the computer science literature, are valid for all problem instances across all implementations, all algorithms. So it's not a matter of that, but it just depends on if you're going to be addressing a small scale problem and you have enough compute power, as we have now, you can make it look like it doesn't matter. And I think that's really one of the problems in the field, is that these functional successes, commercial successes, make it look as if the theory doesn't matter, so people are not looking at it. I think that in reality it does matter, and the comparison then to human intelligence is superficially incorrect, made superficially, and is thus incorrect.
Any other comments from the panel on the issue of scaling and complexity?
Look, P&MP analysis of complexity isn't going to go away, and there are some very hard problems out there. But the brain is the product of millions of years of evolution and has billions of neurons to play with. I think we're massively underappreciating the capacity of that system to have adapted to the kinds of task environments that we're interested in explaining people's behavior in.
Yeah, I would say adding on to that, not only the evolution, but the social cultural evolution means that the representations we use are constrained as well, right? By our knowledge. And this relates to one of the questions that I had in thinking about CRT and cognitive architectures. We start to think and take more seriously representation, which, I say that as somebody who hasn't taken it seriously enough times. I think we also start to think about the way that constrains the problem for us. Naturally as people doing these things, right? And the way that differs from these ML systems that are really operating on PNP, which, in many ways doesn't apply to us because we constrain it. We're bounded in certain ways.
Thank you. So to push on another direction of that, a couple of comments recently and earlier in the chat mentioned learning as a constraint or robustness, and you can think of multi-agent interactions as an aspect of that. And in particular, from the point of view of learning, a lot of the greatest successes of deep RL assume a stable environment, right? A Go board is a Go board, an Atari game is an Atari game. They don't change. And certainly a lot of the insights, for example, of rational analysis early on was that we need to adapt to a constantly changing environment. And that's obviously introduces some trade-off between optimizing to the environment as it is now versus being constantly changing and adapting, perhaps in sort of bounded ways. Any comments on any of these various sort of dimensions of functionality, really?
So I think these are actively explored problems in RL. One approach to handling the issue of non-stationary environments and continuing to drive exploration, to balance exploration and exploitation in a good way, has actually been explored in something we've called the optimal rewards framework. So the optimal rewards question is, what's the best reward function to give an agent to maximize its fitness in some distribution of environments or changing environment? And there are algorithms that derive these rewards and even adapt them online. I'll stick in the chat one paper. I'm actually not a co-author on this paper, but it's a very recent one to come out in this framework that's about deriving optimal intrinsic rewards for exploration over, changing environment dynamics.
I guess related to that, the one thing that always comes to mind, particularly even in RL context, is thinking about classical aspects like simulated annealing and the way they apply so well to thinking about arousal and stress systems in the body and how that interacts with some of the same basal ganglia structures, for example, in the brain. So we can also start to think about how we can make connections to physiological systems and use that to guide the way we look at something like reinforcement learning, right? And it's funny because you can, and I see it in the literature, right? You get to some of the same conclusions if you take like the more theoretical perspective, or if you just look at some of the connections that are there, given the way that RL is connected, for example, to aspects of neural circuits. And so there are multiple ways to approach it, but I think using some of the, particularly since we're in the cognitive architecture related symposium, using some of the things that are there from the body that show us the ways that we constrain attention and representation are particularly useful.
So assuming we don't have any further comments on that particular topic, moving on to something that was specifically prodded from Sean's talk, where he mentioned that learning in LiDAR is only triggered from the conscious context. And by that, I assume he meant the global workspace, which is a little bit similar to, I think, our conception in ACTAR and generally in the common model that consciousness is working memory, the buffers, those kind of things. And I thought initially, well, that doesn't agree with our theory, because obviously there's a lot of sub-symbolic learning. On the other hand, it depends what you consider by triggering. It is the case that a lot of the learning is triggered about what happens in the buffers and the interaction between the modules. So a specific question for Sean on that, but more generally, how much, and Joska Bach also commented on that, how much do we think that consciousness has an impact on intelligence, on the capabilities of cognition? Can you have a human level intelligence or higher without the equivalent of something that we'd consider consciousness, whatever that is? So maybe Sean, you can take the lead on that, and then we can move around to the rest of the panel.
Okay. I guess the last question that you posed there about how basically sophisticated can intelligence be without consciousness, is if I understood sort of correctly. I'm really not sure how to answer that one exactly. I mean, I think consciousness, at least by all appearances, it seems to be extremely important in terms of human cognition and probably other non-human animal cognition. I think it serves a functional purpose. I think there's an adaptive role to consciousness, and we don't fully understand what that is. LIDA makes the assertion, I think global workspace theory makes the assertion that all significant learning requires consciousness. And by significant learning, I'm not talking about priming. I'm talking about, you're not going to, learn the content of, be able to pass a physics exam or something like that by priming. There are certain forms of learning, things that stick around for a long period of time. Anything with explicit, knowledge, that seems to require, the agent to be conscious. And I guess one more thing just to sort of clarify, where we're talking about things like learning skills, procedural learning. Sometimes there's a mixture of terminology in terms of implicit and explicit, calling implicit knowledge, unconscious, but that's not really what we're talking about. If you're learning a skill, you have to be conscious of what you're doing. If you're trying to ride a bike, you're awake, and you're learning how to ride a bike. You're actually conscious of the event of riding a bike. And even though you're not conscious of the product of what is learned, the representations that might result from that process, you might not be able to verbalize them. Consciousness, I think, is still driving skill acquisition and other things that we call implicit knowledge. It's my take.
Anybody else? Well, okay, Rick, Andrew, I won't let you get away with that. Is an RL architecture conscious? Does it include something that we could identify as consciousness or ultimately lead to consciousness? It doesn't commit. Oh, sorry, it doesn't commit to the kind of concepts like global workspace or working memory necessarily, although some of that has been introduced recently that we would identify with something like correlates of consciousness.
I really don't think consciousness is well enough defined to answer the question within the context of this conversation. There's too many competing ideas about what it means. I'm sure Rick has a better answer.
Nope.
So I'll ask a different angle there. So some of the most recent work in that general sort of deep RL domain, in particular, I'm thinking of the work of Bengio, but others as well, is starting to introduce what I'd call cognitive concept into deep learning, right? Things like working memory, attention. Obviously, we had a talk yesterday about attention in transformer architectures, or even playing around with production system type control, right? So the kind of things that cognitive scientists would would recognize. So it's the kind of treatment of sort of deep RL as sort of a pure sort of computational solution, as opposed to the kind of heterogeneous architectures that we've seen. How do you see that space evolving?
Yeah, I think there's a lot of interesting work going on right now that is picking up on classic cognitive architecture ideas, like, rethinking what production rules might be like in a deep RL architecture. Bengio's work, I think, is motivated. Matt talked yesterday about compositionality. That's exactly what's motivating it. And why do RL researchers care about that? Well, they care about sample efficiency, to get back to the concern that Pat's been raising multiple times. And composition, having systems that can compose novel representations, which then trigger, internal mental responses is one way to get extreme generalization and, what's now called zero-shot learning and so on. So lots of interesting things happening there, I think.
Yep. The final theme I had as we're getting to the end here, and that comes from Chris's talk and the emphasis on the social. The concept of explainable AI has been popular lately. The fact that a lot of these deep RL architectures can seem like black boxes, at the very least, to humans that they interact with, whether that's in teaming or any kind of assistance or any kind of relations. Does it matter what's in the box from the point of view of the future of sort of AI and cognitive architectures? Do the inherent mechanism in there really determine part of that functionality, if the functionality includes interacting with humans, or can that be addressed by techniques that provide explainability without changing the internal mechanisms? I think you're on mute. Yeah, go ahead.
Well, I'm going to let others jump in, but I think that there was a talk that started the session 2 days ago on the inner speech, which is trying to give the capacity to an agent to basically give a kind of running commentary about what it's thinking. I think this is a huge area of research that's about to explode, because we now have these, large-scale language models that can, generate human readable text. And so I think what we're about to see is a coupling of those language models with, for example, deep RL architectures, so that the agent is actually giving a running commentary about, the representations that it's using to solve problems. There's a new project that we're working on at Michigan with computer science PhD students here that is kind of taking this to the extreme, which is asking whether we can develop RL agents that just use internal linguistic representations as, you can think of it as working memory, as internal state, so that perceptions get mapped directly into a linguistic representation before it gets passed to an action module. And so it's sort of forcing things to go through a linguistic bottleneck using these large-scale language models. And then we can turn on the speech generation and see what it's see what it says. We're not constraining the language to be interpretable at all. It will spit out grammatical sentences because that's what those language models do. But anyway, I'm just giving that as an example of a kind of approach where the internal representations, like what's in that, the embedded vectors, is not directly interpretable, but there's a component of the architecture that's actually generating speech that is either just running commentary or is actually a crucial internal functional part of the system. John Laird will probably be the only one who remembers that this concept called linguistic task operators, which Alan was, and some of us were thinking about very late in Alan's life. And this is still untapped idea, I think, using language to solve problems. We do it as humans, but we don't have good theories of it. I mean, I think
better include some images in there somewhere too, right, John? Not just linguistic entities. So I think it's very rich possibility.
Well, unless one of the panelists has anything else to any other comment, we've reached the time limit. So maybe I should thank all the speakers and the panelists for a great session. And then hand it back to John for the final word on today's session.